Welcome to a video on applications with algebraic vectors. We're going to do velocity question of a plane with the wind. So this question says, calculate the wind velocity if the plane is known to be moving at 45 meters per second due north relative to the air mass, meaning that this is what the airplane is trying to do, while its velocity relative to the ground, its total velocity or resultant velocity, or what is actually happening in real life, is 38 meters per second in the direction 20 degrees west of north. So we're going to first of all draw what the plane is trying to do. It's steering completely north and going at this speed. And for the direction of the resultant, we are told west of north, so it's actually north 20 degrees west, the way it's written, 20 degrees turn from the north line in the west direction. So if you draw that, this would be it. So we know that resultants, or what actually is happening to the plane, is going to be the plane speed relative to the air mass plus the wind speed added together. So this is an unusual question because we are given the resultant. Usually we're trying to find the resultant. So what I'm going to do is place this resultant right now at the tail of this original plane vector. So then the wind must be attached from the tip and pointing at the tip of the resultant vector. So it's going to be plane speed north, then the wind is going to alter the course of the plane so that the resultant now is this line right here, northwest direction. So because we're trying to solve for the wind vector, we're going to isolate this wind vector and get resultant minus the plane. And instead of doing cosine law, we're going to showcase how to do this with algebraic components. So I'm going to organize this a little bit. We're going to have resultants at angle, x and y components, and then the planes as well. So let's start with the angles. Angles always must be quoted from the positive x-axis. So if we know this angle right here is 20, plus the 90 right here from the positive x-axis, together makes 110. And for the plane, because it's straight north, is going to be 90 degrees there. You have learned that to break it down into components, you're going to have to use cosine and sine of an angle. And so for x components, it's 38 magnitude. So 38 magnitude of the resultant. And multiplied with cosine of the angle at which this resultant is towards the x-axis. And with y component, it's going to be 38 with sine of 110 degrees. For the plane, you do it similarly. So it's going to be magnitude of 45 with cosine of 90 degrees to the x-axis. And then it's going to be 45 is sine 90. So this ends up being 0 here and 45 if you put it into the calculator, which makes sense because it's not going left or right, but it is going straight up at exactly 45 units. So when you're doing algebraic subtractions, all you have to do is create the two vectors and do subtraction between the two components. And roughly when you use a calculator, you would get these two components of the vector. Now you can't leave your answer as this is the wind vector, because if your question is given in a specific format, your algebraic form has to be always converted back to the way the question is quoting the vectors. And so a few more steps to be finished. We're going to draw this vector. So pretend this is a point. It's saying go left 12.9 something, go down 9 point something. Place a dot here and connect from the origin to that point with an arrowhead. This is the wind. To find the magnitude of this wind vector, what you're going to do is use Pythagorean theorem on the right triangle that gets created. And then you would do tan inverse of the y component divided by the x component values. And when you do that calculation, you get a 36 degrees. Now 36 degrees from the positive x-axis is not actually in the quadrant that we want, it's over here. So you can use symmetry to say that 36 degrees must be over here as well. Using complementary angles, you could see that this will be 54 degrees. And so you could say that the wind is now at 16.0 meters per second, 54 west of south, or it could be written in this notation if you prefer. So here's the same question done in geometric way. We've just finished algebraic version. So I have kept my final solution from before over here, so you could see, and I have kept the picture as well. So as we mentioned previously, you could have used cosine law for this picture because you have side, angle, side provided here, and that would give you the magnitude of the wind. Over here, I'm keeping 3 decimal places because I'm going to have to use this answer elsewhere over here. And then I've placed theta at the tail of the wind vector close to the south line or north-south line, doesn't matter which way you call it, just the vertical line. And you could use sine law to find that angle, and you'll notice how you get the same result that way, which some of you might prefer this because it's very similar to what you would have done in grade 10. Let's do another example. In this example, we have a boat being affected by the current in a river. So we have a ferry boat crosses a river from south to north and arrives at a point on the opposite bank directly across from its starting point. The boat can travel at a speed of 4 meters per second in still water. So if there is no current, this is the speed at which the boat can go. So we're told the magnitude here. And then we are told the current of the water is 1.5 meters per second in the direction east. Then you're told how wide the river is, 650 meters wide. And there's 2 parts to the question. Part A, what direction must the boat steer? And part B, how long will it take to cross? So suppose our river is going this way. We have the direction of the current east at 1.2 meters per second. We know that the resultant of what actually truly happens is that the boat goes directly across. That's what the question's saying. It ends up directly across. So because the current has been pushing the boat east, that means the boat was actually steering slightly west or slightly upstream. Then the current pushed it over so that in the end it actually ends up going straight up or straight north. So let's do this again in algebraic way. So we have the current, the blue vector right here. We have magnitude multiplied with cosine of angle 0 degrees. 0 degrees is because it's going straight east. That means the angle with the positive x-axis is 0 degrees. And so sine 0 over here too. And when you do this on the calculator, you'll notice how the sine of 0 is actually just 0. So the vector is just 1.2 comma 0, which makes sense because it goes only to the right and not up or down. The boat vector, we're not told the direction at which it's going upstream, but we do know that its size or how fast it's going is 4 meters per second. So we can just say 4 cos theta, even though we don't know that theta, and 4 sine theta. Then the resultant. We don't know the size of this resultant, but we do know its direction. So here I put in just r without the vector symbol to indicate that this is going to be just the magnitude. Cosine 90. Why 90? Because from positive x-axis it is 90 degrees to that resultant red line. And then if you do these in a calculator, sine of 90 is just 1 and cos of 90 is 0, so you get this vector right here. So how do we know how they relate to each other? We know that the resultant is the boat plus the current together. And if you use the algebraic component vectors and create an equation out of that, you can then break it down and work with it just x components separately. So 0 equals 4 cosine theta plus 1.5. That gives us this equation. For y components, you would say r is equal to 4 sine theta plus 0, and that gives us this equation. This equation here has two unknowns, r and theta. This equation, fortunately, has only theta, so we could solve for this theta, and we would have an obtuse angle. This theta is always quoted from the positive x direction, so it's this obtuse angle right there, 112 roughly. Then we can use this solution in the next equation. Notice I'm keeping 3 digits of accuracy here because I don't want to round too early because I'm not finished yet. And so that gives us the magnitude of the resultant. And so I think we are ready to answer part A. It says, in which direction must the boat steer? So we actually want to know how far upstream it is, not this full angle, 112. So we want to know this part right here. So if we subtract 90 from 112, we would get 22 degrees upstream from the directly opposite where it wishes to arrive at. So just be very clear exactly what you mean by the 22 degrees upstream. And finally, how long does it take to cross? So we know that distance, speed, and time are related together with an equation. So time is equal to distance divided by speed. So in order for us to do this calculation, you have to make sure you grab the velocity that corresponds to the distance. So the distance 650 is the vertical distance because you're told this is 650 meter wide river. So you cannot just take any velocity that you wish to divide. So you cannot take the original boat velocity 4 meters per second to divide with into the distance, because this green arrow is not in the same direction as the width of this river. So you have to make sure you grab the corresponding sides to do this division, and you would get roughly 2.9 minutes that it takes to cross this river. As a comparison, let's do the same question with geometric way, which is also very simple here. So I have kept my solutions from before here. I have kept my magnitude and angle from before. This is the new stuff I've adjusted, so you could see, you could always pause and take a moment to really read this. But briefly, to discuss it, we have a 90-degree angle triangle here. And so we could use just pure Pythagorean theorem to isolate for what the magnitude of the resultant is. And we do end up getting the same result as before. And then we want to know how far upstream should the boat be directing itself so that it does end up directly north. So then you would find this alpha using SOHCAHTOA. It ends up being sine of alpha is opposite over hypotenuse. That's the two things we do know. We can isolate for alpha and we get 22 degrees as before. So you're welcome to use whichever method you wish. I'm just showing you how you could use algebraic components to solve exactly the same questions as we've done in the past. So lastly, if you have multiple vectors, more than 2 vectors, then I would, like my preference, I think would be to go and do this in the algebraic way. And let me show you how. So I'm going to do it algebraically, but then I'll also briefly discuss geometric way, and you'll see that it gets a little bit more confusing doing it geometrically. So let's start with vector A. We're told it is 37 degrees east of north, so this is the picture of it. And because we want to quote the angle close to the positive x-axis, the theta over here will end up being 53. The x component would be magnitude of the vector times cosine of the angle. And then y component would be magnitude 12 and sine of the angle 53. You do the same thing for angle B. So angle B is 50 degrees east of south. So this is the picture of it. We want to quote the angle from positive x-axis. It goes all the way around almost full revolution, but not quite. So it's 270 degrees of revolution plus the 50. That gives us 320. And then the components as before. Lastly, vector C, we have 30 degrees west of south. So this is the picture. We want to quote the angle from positive x-axis. So that would be almost 270, but 30 degrees less. So you could do subtraction in this case. And then its components. done over here. If I went too fast, you can pause and take a look at it and digest it, okay? Next, what we want to do now is to find the resultant force between those three vectors. The resultant would be addition of all three vectors. Now, because we broke it down in algebraic components, all you have to do is add all the x's and then add all the y's, and you would get this approximately component form. Again, because the original question did not have algebraic vectors, you want to place back your solution in the same manner that the question was phrased. So what we want to do is now just convert this back to geometric form. So I'm going to draw the point. So even though this is not a point, it's a vector, we can think of it as a point. So we're going 15.7 to the right and 5 point something down. Place the point, connect the vector from the origin to that point, and draw an arrowhead. So now let's find the magnitude and direction of this vector. So for magnitude, you could use Pythagorean theorem. For the direction, it's always going to be tan inverse of the y component divided by the x component. That would give you a negative angle because we had a negative inside here. So what does that mean? This means that this angle is going from the positive x-axis, but going in a clockwise direction instead of the usual way that we rotate at negative 18 degrees. And because we want to quote this in relation to north-south line first, we can find alpha angle using complementary angles with the 18 degrees. And then we can say that the resultant. Oh, I just noticed that I changed the question to be about forces so I could talk about equilibrium, but I forgot to change the units. Forces are always measured in newtons. So instead of meters, pretend I always had newtons here. So the resultant vector force would be 16.5 newtons at a direction of 72 degrees east of south. And the equilibrium is going to be the opposite of the resultant force, so negative of the r vector. And all you have to do is just change the signs of the components on the inside. And if you were to draw this, it's going to go in left and up. And so you can see how it's exactly opposite direction of the resultant. So this would be the equilibrium force. And if you quote it in geometric version, so these two are algebraic versions, these two right here are geometric versions. And so this would be the same magnitude, but the direction south flips to north and east flips to west. Now, we're going to do the same question, but I'm going to briefly discuss how you could do this in geometric way using sine law, cosine law, and to show you that it does get a little bit more crazy with three vectors other than the two that we usually have. So first of all, I'm going to move the vector b that I had. So let me go back so you can see. So this was vector b. I'm going to add a and b first together. And so reorganizing them tip to tail, and this would be the resultant vector number 1. So it's not the true resultant yet, but I'll call it R1. This is my final resultant from the previous slide. I'm going to keep it here so we can see if we get the same result using this other method. So I'm going to jump a lot of steps right away, so feel free to pause this to take a look at the information provided. So what we have here is we want to find this angle in between this green and the red. Well, we have partial angle 50, and then we have a Z pattern over here that we could say that this angle right here is 37. So if we add them together, we could say that that's the angle 87 that we could be using in this triangle. So we have side, angle, side, so cosine law for the magnitude of this purple vector. And then if you place theta at the tail over here, you could use sine law to find that angle. However, what ends up happening is that if you think about this angle right here, this 37 plus this theta. So if we were to add 37 plus the theta that we got with all the digits, or at least 3 digits of accuracy, you'll see that it slightly goes beyond the 90-degree angle. So the diagram is not quite right. So if you do it with a geometric version method, you have to really pay attention how you draw the diagram and verify whether your answer makes sense to it. So I'm going to fix it a little bit. I'm going to slightly go beyond the 90-degree angle here. Just change my red vector as well, just to match it up. And so then when we quote this vector, then you could see that it actually goes in the south direction. So you cannot just assume because you had it pointing north that you have to say northeast. In this case, it ends up being southeast. And how did I find this 89.822? Well, you could just take that little slip of an angle here and subtract it from the 90 to get that it's just slightly below 90 degrees. Now this is not finished because we still have to take that vector c. So let me move it back. So this is how it is here. So now I need to move this vector c to the tip of this purple vector and add it together and get this blue vector. And this resultant should be the same resultant we had before. So let's see how that could be found. Again, feel free to pause because I'm just showing all of this at once. Briefly to discuss it though, we have alpha angle, which is between the x-axis and the purple line. You could use Z pattern to find that this alpha is over here as well. And that alpha is that tiny angle we've discussed before. And then to use the cosine law on this magnitude of r, we have to do alpha plus the 60 degrees. Where's the 60 degrees coming from? Well, this right here would be 60-degree angle because this angle right here is 30, so they're complementary with each other. So if you do this calculation of cosine law, you will get 16.5, which we had previously, so that matches. Then to be able to find the angle of this blue vector, we want to place another angle within the triangle, but close to the tail of the vector that you're looking at. So I called it angle beta, and you could use sine law on that, find that angle beta ends up being 18 degrees. And then, because you want to quote it in relation to the south line, I call this angle right here gamma. And to find gamma, it would be 90 minus beta minus alpha, because that's the complementary. There's that 90 degrees gets split up by alpha, beta, and gamma. And so you would get the 72 degrees, which we did have before. So this whole video is to show you two ways of working with application questions. If you have two or more vectors, algebraic method might be more convenient, but you are welcome to do either methods. As long as you show your work and justify everything, you should be fine and get all your marks.